Hello, good evening. This is Professor Khan, and this is Energy System Technologies EST-204 Heat System Design, and we are in week 8, or I don't know, maybe week 9, but the week after the midterm. And today we're talking about heating. What are the possibilities for us to do some heating in a house? What are the options? And we already covered appliances, lighting, and now we will do heating, and next week we'll do cooling. What are the options for heating a house once we do the heat loss calculation and know what is the BTU required for that house per hour? So let's start, and hold on, there we go. Okay, so this class will learn about residential heating options. What options do we have? And again, I want you to remember that there is no one size that fits all. Every situation is different depending on the preference, also depending on what is available, what is the price of the fuel, and how much you need to heat the house. So there's a lot of options, and it's good to know what are the options and what are the alternatives we have out there. Second, we'll talk about the concept of efficiency. Efficiency is a widely used term, and we would like to know what do we mean when we say it's efficient. And usually we talk about the fuel, but there's a lot of efficiency that we have to be aware of. And being a technician, it's good for you to know what do we mean by efficiency and how does it account into when we talk about efficiency and we tell somebody, hey, this system is more efficient than that, we should be careful what we are saying so we do not convey the wrong information. We'll also understand the convection heat transfer using air or water. We did talk about the three modes of heat transfer, and we said there's convection, conduction, and radiation. And we'll talk about convection heat transfer using air or water. Also, we would like to trace heat transmission inside a system. The heat transmission, trace the heat transmission of heat inside a system. Meaning, if you burn some fuel or you generate some heat inside the furnace, you want to trace how would that carry out all the way to the space that you need it to be. So types of heating we have this is what we have available so far. We have gas, so we can either either we can use gas. Okay, this thing's off. Use the mouse. Gas. That's actually if you have supply of gas, or sometimes you can have butane gas. Gas could be natural gas, it could be a blend, or it could be butane gas or propane. So that's gas heating, and again, that's part of combustion. Oil is also combustion, and it has advantages and disadvantages over gas. We also have wood, like wood stove, or pellet stove, or just firewood. So again, those three are all combustion. We are burning something to get some heat. Then we have electric heat, which can vary from 35% to 95%. What does that mean? For electric, we can use a heat pump, or we can also use coil. Coil is transferring heat from electrical energy to heat energy. So coils are very efficient when it comes to transfer because the direct transferring of energy, and there is less losses. But again, it's very expensive, so it's not going to be efficient for your pocket and money-wise, but it will be efficient when it comes to energy transfer. So efficiency usually is output over input. What did you get out of how much you spent? And it's good to compare things that are actually, it's important to compare things that are similar. So we're comparing energy to energy, or conversion of energy into dollars. So how much did we put in versus what we got out? So try to remember that efficiency is input over output, and what are we comparing to what? So for example, if we talk about a boiler and say this boiler is 95 efficient, what are we comparing here? Are we comparing the efficiency of burning the fuel, changing the fuel from chemical energy into heat energy, or are we comparing the amount of heat we're producing in the boiler to the amount of heat we are sending into the house? So there is something called thermal efficiency, and there is combustion efficiency. Combustion efficiency can never go above late 80s, maybe 90 tops. But if we talk about thermal efficiency, that could be up to 99, meaning all the heat we have made and generated inside the boiler has been transferred and absorbed into the system. So there is thermal efficiency and there is combustion efficiency. So talking about fuel, what do we use? Again, this is from the book and this is almost 10 years old. So probably things have changed a lot. So gas heat is very common. I don't know why is this doing this, but fine. So gas is very common in the Northeast. We have electricity, meaning using heat pumps, or coils. Those are very common from states below Washington, D.C. when there are not a lot of cold days. Oil is 9%, mainly also in the Northeast and in places where there's not a lot of connection for gas. And others, by others we mean wood stove, biomass, different kind of fuel oil, and so on. So losses, again, this is again talking about efficiencies. So this is the burn efficiency. Like we burned the fuel and we got something out of it. Excuse me. So we burned the fuel and we got most of the heat out of the fuel. Where does the efficiency go? If you look here, there's 1% losses, which is unburned fuel. So you usually cannot burn the fuel completely. There are some byproduct come out of the fuel. This is something we lost. Then we have losses here. Sensible heat. We lost some of the heat to losses in the boiler, losses in the pipes. We have excess air heat losses, latent heat losses that comes as condensation. Off cycling, there's also some losses. And between the heat, so if you look at the heat here delivered to the house or the living space to what we burned, it's 40 to 85%. That's a big gap. So it could be 80, it could be 40, and it could be 85, and that is up to you. And how do you select your equipment, and how do you account for all these losses over here? So we want less losses. Okay, moving on. So background, when we start having heat inside the house, they started again with steam as the power and the driving force for heat. We started with the steam to heat places. We realized the steam power, and even back in the days when they tried to heat a house, they will have a wood stove and they put a pot of water on top of it, and the steam will heat and disperse the heat over the house. And if you realize that steam has more power than air, have a lot of moving power. Like if you have an empty pot and you heat the air, it's not going to move anything. But if you have a pot with a lid on it and you have water inside, probably the lid can be pushed by the steam inside. And steam was used as a vacuum pump to move trains and move combustion engines. And the steam engine started by James Watt, and this is when we were able to utilize the power of the steam into moving stuff. So then we went into space heating. Again, the primitive way of heating a house is having a stove inside the house, and you might have some kind of extension of that stove, or like exchanging airs from one space to another, or putting a pot of water on top of the stove to heat the house. But again, that was not very efficient. Then we came to space heating using direct steam into the room. And I put a question here: what could be the problem? It's going to be a little bit uncomfortable, right? It's going to get wet. It's going to ruin your furniture. But this is how it started. We will just pump steam into the house, and when it gets uncomfortable, we open the windows, and you can see there's a lot of losses involved in that little apparatus. So then we thought about putting steam inside tubes and radiation using radiators. That started in the 1820s. So then the American inventor Stephen Gould in 1845 introduced the self-regulating boiler and the practical radiator design, which called the mattress, because it does look like a mattress, like loops of tubes connected to each other and steam going through it. And we still actually have a lot of these steam systems in practice now. His son Sam improved the concept and started his H.B. Smith company. And this actually was started in Springfield, Massachusetts here. So again, the residential heating started in this area, in this state, and in this city, and spread out all over the country. So we built the first boilers here, and we still have that museum somewhere. So steam was the first driving force, and if you go work in heating systems here in Massachusetts, I mean in Western Mass, you'll see a lot of steam. It's still working. It's still running strong since the earlier this century. So why did we start with steam and not water? And now if you go to new installs, you will hardly ever find any steam. It's going to be all hot water. So the reason being is steam did not need a pump to move. It will move by itself from high pressure to low pressure. So that's why I started with the steam. The invention of pump came later, and with the pump we were able to heat water and not have to make steam and circulate the water around the house. So the pump came with the invention of electricity and motors and made life a little bit easier. Steam is not no longer used because again it's a little bit dangerous. Having steam under pressure is dangerous to have in somebody's house. So a lot of houses that have steam, they still have it, but if not, the new installs mostly are all water. So introduction of the pump was introduced in the 20th century. Water is used as a heating system, and it's called hydronic from the hydrogen that drives the water. So hydronic is a steam system. So hydronics is a common term that includes hot water and also steam. Electrical controls were added to the system, which is something you're going to be working on, which is the aquastat, the high pressure cutoff, low water cutoff. All these controls were made to make the steam system work more efficiently and make things a little bit easier with least human interaction possible. Piping did advance a lot since then. If you look at the old system, probably you'll see a lot of thick old steel pipes, and now you see thinner pipes and more elaborate piping configuration. Radiators, they have new shapes, new materials, lower cost. Steam radiator was very heavy and it has to be pre-ordered per section, and the estimation for the radiation for steam was very elaborate. So now we use radiators. So again, for new installs, probably you will do more hot water than steam. Okay, for us to make heat, we said we have either two things. Either we use heat pumps or we can use combustion, which is burning stuff and making heat. So coal, still very common. Coal is king, still very common and has a lot of energy. And the energy we get from coal is 55,000 BTU per pound, depending on the type of coal. Problems, shutting down and starting is a big problem. How to regulate coal for heat? It's a little bit difficult, much more involved than using propane. And I was giving the example of comparing propane grill to charcoal. With propane, you can lower and turn up the heat. Meanwhile, with charcoal, you have to add more charcoal or like dampen the heat or so on. Startup is an issue. We always have to think about starting up the coal. It's not like starting up gas. With gas, you just like light it up with a match and it's gone. With charcoal, you have to start with one piece of charcoal, build a little permit and blow on it and all this kind of procedure. So it is a little bit involved, although they did make it into pulverized coal, which is easier to ignite, but all in all, it's still a little bit more involved than gas or oil. Cycling is a little bit difficult. It's not as feasible. It's a waste of fuel to turn them up and down. Then we have fuel oil, which is diesel or biodiesel. They're both the same. They have the same properties, and they have around 138 BTU per gallon. 1 gallon is around 7 pounds, so you can say per pound, comparing pound and pound, is like pound to pound is a little bit less than, a lot less than coal. Wood pellets, they provide you with 8,500 BTU per pound. Wood pellets are convenient. They're kind of easy to transfer, but again, they're not very abundant sometimes, and the price does fluctuate a lot based on the production. Natural gas, 8,600 BTU per gallon. And finally, we have electrical heat, and I'm talking in this case about coils. If we have a coil that gets heated and air or water go through it, it's around 3,400 BTU for kilowatt hour. Kilowatt hour is around like 20 cents, so you're paying 20 cents for 3,400 BTUs. It's a lot. Here's a link for some references about these conversions if you're interested to know more about them. Okay, some conversions again. So combustion, air is 21% oxygen, 79 nitrogen. Please try to remember that. It comes up. This question comes up a lot when you do the test for uh, oil burner technician license. They will always ask you what is air composed of. So it's good to know it's 21% oxygen and 79% nitrogen. Why do we need the right mixture of air and fuel? So again, I'm trying to get you to think about the byproducts. And when you make a fire, you're looking for light or you're looking for heat. You're not looking for the soot, right? This is the byproduct that you don't want. So if you have too much air, you're gonna have some soot and smoke, and if you have less air, you're gonna have the same problem. So you would like to have the right amount of air to burn the fuel. There is something called secondary air and primary air. Primary air is the air that you introduce with the fuel. Secondary air is the air that also gets sucked in once the fuel starts to combust. So you are consuming the air and you want some inlet for the air to come in to substitute for that. This is the equation. It's a little bit involved, but we can look at it from a simpler point of view. I mean, if you look at that here, look at the this basically is hydrocarbon. It's hydrogen and carbon. It could be anything. You know that gas, butane, propane, and fuel oil, charcoal, they're all hydrocarbon, which is a combination between hydrogen and carbon. O2 is a nitrogen, this is air, and spark, which is the beginning of the heat. Then you will make a fire, and the fire will make heat, carbon dioxide, water, which is the condensation, and nitrogen comes out sometimes as is, and sometimes it becomes into nitrogen oxide, and you also get some sulfur oxide with that oil. So sulfur oxide is a byproduct of hydrocarbon. Mostly petroleum products, they have this sulfur in it. So again, we have low sulfur in this country, but burning fuel oil usually comes with sulfur. Common terms for heat, so BTU, we talked about that before. It's energy to raise 1 pound of water 1 degrees Fahrenheit. We also have BTU hour, which is a lot of BTUs in 1 hour. Calories, again, calorie was compared to BTU a lot, is to raise 1 gram of water 1 degree Celsius. And we also, in food, we actually measure kilocalories. So it's kind of interesting just to know the conversion and how much calories needed per day for a human being. Usually they estimate around 2,000 calories. Horsepower is around 2,542 BTUs. Commercial boilers go with the boiler horsepower. That's another thing which is different. It's 33,500 almost BTU hour. So you'll see that with big boilers. SI system, which is System International, and the rest of the world uses SI, but in the US we still use BTUs in the imperial system. So it's good to know the conversion between kilowatt and BTU. Burning fuel. So we can burn gas, oil, or pellets. This is the main idea of combustion heat. And if we look, this is what we are doing actually. Basically, if you look at any boiler, any pellet stove, it's closed. You don't see the fire. Things are happening from the inside. Your primary air and secondary air comes in with the fuel. You burn it, then you discharge all the combustion air outside. And you get some kind of air inside here to eliminate the vacuum. I don't know why it's doing that again, but fine, whatever. Okay, so this is the air comes into the chimney to make up for the flow. So you don't have a vacuum and you don't have some backflow. So usually your fuel comes in here in the boiler. You're going to introduce some air to it, and you do all your heat exchange inside the boiler. We're actually heating either fluid, which is air, or water. Could be liquid, could be gas. So we heat our fluid to absorb the heat that came out of combustion, and we take it wherever we want it inside the house. Another term that you need to know is a sealed versus open combustion. When we do open combustion, we're taking air from the house and throwing it outside. So probably you thought you need to introduce new air into the house. Otherwise, where is this boiler going to get air from, right? So to solve this problem, if you don't have a lot of incoming air into the house, you might need to do sealed combustion, where you take the air from the outside and you throw out the air, the combustion air to the outside. So this is a sealed design where you have the incoming air coming from the outside, from the same opening here, and you do the combustion and things get thrown outside. So you'll see that in a lot of gas. Mostly the new designs, they come with an intake and outtake pipe together, completely sealed, and nothing comes in from the house, which I prefer this as a new installs because you don't want to depend on the opening inside the house to provide your combustion air. So gas furnaces, they're very common and they're very easy to couple with AC. They're very convenient for us. We can put a heat exchanger or a coil on top of here, and that a coil will help you cool in the summertime, and in the winter you can use the gas to heat the furnace. It could be a gas furnace, could be oil, but this is the air handling unit. And you can also use gas to heat water or air. More about the sealed combustion and the vents. Uh, so let's think about convection. So we need to transfer the heat from the source to your living space. So you can use hot air system where you heat the air and bring it all the way to the living space. And actually we breathing air, we are in contact directly with air, so it's very convenient, it's very fast because you're gonna feel the hot air right away. It's again quick, it's easy to couple with AC. However, it has more losses, and that depends on the design, so it's not always the case. And by versatile, I mean it does cool, it can heat, it can remove particulates, it can put a filter. So basically you're air conditioning the air inside the house to be the way you want it to be. Okay? And there are no visible radiators, which is an advantage. As a disadvantage, it requires humidity control because it does drive the air, and it uses forced convection, which means there is an inducer fan somewhere, and that inducer fan can be either pumping air into the room, it could be far away, but it could be noisy, and some people do not like the draft. Also, it circulates more air, which is also can be considered as a disadvantage. You will get more dust and more circulation. I mean, if you don't like it, then it's not going to be something you want. And it can be a little bit costly, and that is because you will need to install duct. Okay, moving on. We have here this is duct system again, and an example of duct system. I will talk about that more elaborately next semester. What type of plumbers do we have? What type of connections? And being a sheet metal worker is a very, very desirable trait to have in a technician. If that's something you like to do, please invest in it, because again, we are having less and less technicians who can properly do duct system, and we will need to have ducts. If you're going to do an elaborate air conditioning or heating in a system, you need to have the proper duct to go through it. So that's for heating air. Steam and water, it's hydronic. That's what we call hydronic. So we can heat steam and send steam to radiators, or you can heat water and send the water through small finned radiators, and they both are very quiet. We're heating water or steam, and the steam will interact with, or water will interact with the radiator. This will get hot, and this heated fins here and here will eventually heat the air, and it is natural convection because the air gets heated and it rise by itself and drops again when it cools. So it's called hydronic. Advantages: it is quiet. You don't usually hear it unless there is a bad design and you hear a lot of swishing or banging in it. It's more efficient. Again, efficiency is always a relative term because you have to think about the energy you put into the house and what heat are you getting out of it. It uses natural convection, and it can be a standalone system, and some systems actually they don't even require electricity. So that's again another advantage. Disadvantages: there's the possibility of leak or freezing, which happens if you don't follow the right procedure into shutting off the system in the winter or draining the system out of water. The radiator location can be an issue. Again, it has sometimes you need to long radiator to go all around the perimeter, which is again not something desirable for everybody. Again, we said the possible freeze is another issue. Steam radiators are kind of big and they get a little bit too hot. So if you have children, and it can be as hot as 200 degrees Fahrenheit. So it's very dangerous to touch a steam radiator, especially if you have kids in the house. So usually they come with this fancy cabinet, so you can put around it so you don't burn yourself. Excuse me. Again, some piping schemes for hydronic systems, be it steam or water. You can look at that. There's some more elaborate pictures in the book, and it gets a little bit like involved when it comes to piping the system, and it's something you want to do when the house is just being built, because most of those pipes are done inside the walls. They're not very visible, so it's not something you will put as a retrofit usually in an old house. A lot of people, when you try to go and put an addition or something, probably you see people trying to peg into the same system by putting a extra loop, and it's not always a good idea to do that. It's good to have a standalone system, because probably chances are the system is sized. If it was sized correctly, if you add something to it, probably it will be undersized, and that's not something you want to have. So steam has advantages. It's similar to water. It has faster heat, because again the water is heated up to like 220 when it becomes steam, and it's easy to control and zone. If you don't want to heat one room, you just shut off that steam radiator in that room, and the possibility of freeze is lower than hot water, because all the water goes back to the basement. Again, leaks and rust are issues, and the mattresses are very big. It's called the mattress because it does look like a mattress, and it is an issue also for extra pressure. Again, if you're building pressure, that's a possibility for a system to explode or have terrible malfunctions. And again, we said steam has a lot of power, so it's a little bit tricky and require a lot of safety valves and safety measures. Here is the gravity steam system. Probably again you'll see it again, and remember this little loop here, it's called the Hartford loop. So the biggest problem with the steam system, whether it's two pipe or one pipe, so we have the one pipe here and the two pipe here, is you don't want the steam to run on dry. This is when it starts to build heat, and you might build up some steam and it might crack your boiler. So there's a lot of measures to counteract that issue. The Hartford loop is one of them, to maintain the water inside your steam in case you have a blowback. Also, you want to have a low water cutoff if the system has some kind of leak. You want to be able to shut down the system and prevent it from working when there is a leak going on. Wood stoves, they're very common, especially for new additions or basements, or like if somebody have an unfinished basement and they want to add some heat to it. Usually they put a hot stove, and again heat always rise up. You can burn wood here or pellets, and again it does need some intake and outtake. So the intake usually is incoming from the house itself, from the house itself, and this is how it vents outside. And these pipes actually can be used to emit heat. So we are combusting the air, and we're heating the pipe at the same time. So you can use this pipe to heat 1 or 2 stories as we go along. But you notice in this area here that this pipe gets really hot. So whenever it's going through the ceiling, you want to have a lot of kind of insulators support, so it does not get very hot and ignite those combustibles. So it's something that you want to follow the local code before you install to make sure that's not going to hurt anybody or like be a fire hazard. So look at the textbook. There's a lot of new ideas. I have not covered some of the information about heat pumps, which are becoming very, very common for heating. But the reason that we cannot rely completely on heat pumps is they do not give us efficient heat during the cold months of January and February or even March. And again, when I talk about efficiency, meaning the power consumption divided by, I mean, the output of heat divided by the power consumption. They will consume a lot of power, meaning electricity, to give you some little heat. That's when it comes to heat pumps. Electrical coils, yes, they are efficient, but again, they will cost you a lot of money to heat your house using electricity. Okay, this is what I have to you for this week. Please read the book and let me know if you have any questions. Thank you.